Well, thank you, Richard. It's really an honor for me to share this podium with you. In my career on Wall Street, I had good times and bad, and during the bad times, I never had a client who called me up and said they were praying for me. I wish they would have, but usually we had more difficult conversation than that. I guess if we can bring the first slide up. My topic tonight is pricing climate risk. And carbon dioxide and other greenhouse gases are flowing freely into the atmosphere around the globe these days because emissions created primarily from burning fossil fuels are not currently being priced. The resulting growth in the level of greenhouse gases in the atmosphere is creating an exponentially growing risk of a very significant long-term degradation on the environment. Carbon emissions should be priced because they embed this externality. They increase the risk of a climate disaster. The logic is very simple. Not pricing risk leads to too much risk being taken, and too much risk being taken leads to disasters. The only question really is, where should emissions be priced? What's the appropriate level? And that's an interesting story. It's a story of economics. And it turns out the economists who are debating this question are leaving out two key considerations: risk aversion and unknown risk. Let's start with risk aversion. The issue they're trying to address is where to price risk. Risk aversion is central to that question. And yet the models economists have been using to price climate risk have not been calibrated along the risk aversion dimension. Rather, as we shall see, they build in a risk tolerance that is totally inconsistent with what we see in financial markets. And we know why they do this. Incredibly, in the standard economic model that economists use, the utility function is such that when risk aversion goes up, the appropriate price for carbon emissions goes down. This property of the standard utility model makes no sense. Now, in fact, there are more modern, more general utility functions that can capture risk aversion properly. In those models, as risk aversion goes up, the appropriate price for carbon emissions also goes up. And later I'll show you an example. And in those models, we can, at least roughly, calibrate them to financial market prices. Again, the second big problem with most economic models being used to price climate risk is that they ignore unknown risks. What economists do is they take the risks that they know about, they look at the damages those risks might create, and they present value them. When you're running an experiment for the first time, particularly on a very complex system, the Earth's environment, things can go wrong. And there are unknown risks. When the issue is where to price risk, you can't leave out a whole class of risks and just pretend they're not there. At best, such analyses provide a lower bound on the appropriate price. But if we want to answer the question, what is the appropriate price, we have to include all of these risks. And I'll give you an example of how this can be done. My talk tonight is a challenge to economists, really. There should be a debate among economists about what is the appropriate price for carbon emissions, a serious debate. And in that debate, we should pay attention to two key issues. One is, how do we calibrate risk aversion when we're pricing climate risk? And secondly, how do we model the unknown risks in this experiment with the Earth's environment? And finally, let me share some intuition that I have about how to think about the appropriate price. Because not only is it the case that when risk aversion goes up, the appropriate price for carbon emissions goes up, as we shall see, it's also the case that when risk aversion goes up, the forward curve, the future price of carbon emissions relative to the current price, goes down. Higher risk aversion pushes down the forward price, the forward curve. And ask yourself, how high would the price of emissions have to be today for you actually to expect it to decrease in the future as we get more information? It's pretty high. Now let me start out by asking a very simple question. Why should prices in financial markets inform the debate over where to price carbon emissions? Think about what pricing emissions is. It's recognizing the impact of our actions today on the distribution of damages in the distant future. Think of those damages as negative cash flows. Pricing emissions is discounting that set of uncertain future cash flows. It's exactly the same task as pricing an equity, discounting a set of uncertain future cash flows. The high observed premium for equity risk is clearly the appropriate metric as we calibrate the level of societal risk aversion in our models for pricing emissions. What financial markets tell us is that society, in its investment decisions, is incredibly risk averse. Clearly, the higher is the level of societal risk aversion, the higher is the appropriate price to pay for reducing climate risk. What makes this story so fascinating to me is that to date, economists have been ignoring this obvious implication. For example, listen to the following recent quote from a leading climate economist. It was taken from an article published just last month. He's talking about the required rates of return on investments in reducing emissions. And he says, quote, "My view is that the return on capital is high, so that the threshold is pretty high if we're going to compete with other uses of our investment dollars." Now that may sound reasonable, and it is up to a point. This economist makes the very good point that capital is a scarce resource, and to determine how much we should invest in climate mitigation, we should evaluate the benefits that we get from that investment. And we should compare them with what we get from comparable investments. So far, so good. The problem here is what comparable investments means. This is an area where the economics profession, and especially the group associated with Minnesota, has made tremendous progress in the last 30 years. As I'm going to show, the tools developed by this group of economists show that an investment in climate change mitigation is not like ordinary capital investments, very risky and demanding a high discount rate. Rather, it's more like an investment in an insurance contract for mankind. Also very risky in a sense. It may or may not pay off, but for which, as risk aversion goes up, the payoff should be discounted at a lower rather than a higher rate. The reason higher risk aversion raises the bar for equities is because cash flows created by equity investments are most likely to occur in good times, when marginal utility is low. The reason higher risk aversion lowers the bar for climate mitigation is because the benefits of investments in climate mitigation are most likely to occur in bad times, when marginal utility is high. I was trained as an economist here at the University of Minnesota over 30 years ago, but for the last 25 years, I've been a financial engineer on Wall Street, working on issues related to pricing risk. On this project, I've had the incredibly good fortune of working with an exceptional economist, Kent Daniel, a former University of Chicago professor who's now teaching at Columbia. Before I start, I want to make two caveats. First, some of the economics is a bit technical, and I've tried to keep this presentation at a very high level, so I think you will be able to understand it. And second, Kent and I are both experts in pricing risk, but we're not experts in climate science. So while we know that the two considerations I've mentioned, risk aversion and unknown risks, will both increase the appropriate price for carbon emissions, we can't tell you what that right price is. And finally, let me be clear, it's not my intention to suggest that there's anything new, any new finance here or economics or climate science. We're simply pointing out what we think are some rather important implications of well-known principles of pricing risk, many of which were developed over the last 3 decades by folks from the economics department here at Minnesota and at the University of Chicago. So the story starts in Cancun. You may remember the UN climate conference there in November. At the end of it, Mexico President Felipe Calderón suggested that global warming is like a passenger bus careening out of control down a steep mountain road. And he said, we need to brake as hard and as fast as we can. Was President Calderón right? Well, let me tell you a little bit more about pricing risk. First of all, the brake that he's referring to is the price of carbon emissions. And if you want to put that in context, I don't know if we can see that very well, but basically the current price of carbon emissions is globally about minus $10 a ton. And that's because there's huge subsidies. The International Energy Agency, it's not particularly an environmental friendly group, they reported recently that in 2009 there were over $300 billion of subsidies of fossil fuel in the world. That's $10 a ton. Now in the US, the current price is about zero. The current price in Europe is about $18 a ton, but when you take it all and add it together, it's clearly a negative price. In other words, we're currently not braking at all. We're accelerating as we go down this road. What's the appropriate price for carbon emissions? Well, it depends on two things, risk and risk aversion. And we know as risk increases, the appropriate price goes up, and as risk aversion increases, the appropriate price goes up as well. Now, it's a complicated problem, but people actually have a pretty good way of developing an intuition about this. In fact, people are able to solve problems like this very quickly in their head. Think about dynamic optimization in a context where there's uncertainty, tipping points, nonlinear responses. It's like going down a hill. When you're on a bicycle, I like to bicycle, and I like to bicycle in the mountains. When you're going down a steep hill, you're constantly on the lookout for risks. And when you think you see something new, perhaps there's something in the road, it's wet or it's getting steeper or something, you quickly form in your mind, virtually instantaneously, in the fraction of a second, a plan for how you're going to respond. Maybe you're going to brake lightly, maybe you're going to brake very quickly, maybe you're going to slam on the brakes. What does it depend on? It depends on your perception of the actual risk, that you might go off the road or whatever, and it depends on how risk averse you are. Now, in the debate over where to price climate emissions, some economists tell us, don't worry, we'll start braking soon, and that curve is way down the road. We'll take care of it. It's not a big problem. Other economists say, no, it's a big problem. We should get started right away. Unfortunately, these economists have not, in their thinking about risk aversion, in thinking about pricing emissions, taken risk aversion into account appropriately. We're going to address 4 questions here tonight. First of all, what is the appropriate price for emissions? Secondly, what does the forward curve look like? Is it upward sloping? Should we expect emissions prices to go up over time or to come down over time? Thirdly, what's the cost of not pricing emissions appropriately? And finally, how quickly should we move the price to the appropriate level? Now, let's think about the equity risk premium. This was called a puzzle back in 1985 by University of Minnesota professor Ed Prescott and his co-author Raj Mehra. And what the equity risk premium puzzle is the fact that investment behavior reflects extreme risk aversion. What I'm showing you on this slide are 2 lines. They're trends fitted to the log of total return of stocks and of government bonds. The lower line, the green line, is fit to government bonds. This is a log scale. So what that line represents is the average annual return. The slope of that line is the average annual return on a risk-free investment. These are they take real returns, they take inflation into account, and you get about 2.5% over the last 125 years from investing in risk-free bonds. If you had invested in the stock market, your annualized real return over this period was about 6.5%. That difference, the difference in the slope of those 2 lines, is about 4% per year, which it turns out represents very high levels of risk aversion. I wish I had more time to talk about this. It's a very interesting topic. I brought here a book. This is the handbook of the equity risk premium. 600 pages of heavy-duty math. I highly recommend it if you're interested in the equity risk premium. actually my advisor, Tom Sargent, is quoted on the back. He says, understanding how to interpret and capitalize on the large observed equity premium is a central task of macroeconomics and finance. Well, we're going to use this equity risk premium tonight and think about what it implies for pricing carbon. Again, the puzzle is that investment behavior represents extreme risk aversion. And by the way, the message of this book, it's still a puzzle, okay, after 25 years. Now, why do you think the premium is so high? I think most people would say, well, it represents the volatility of equities. Obviously, you can see the blue line there. It is much more volatile than government bonds. It turns out that's not the case. If we add another line to this, here's a return series that's just as volatile. In fact, you may notice there's a pattern. This is the returns you get from being short equities. And if you adjust this portfolio so that it has the same volatility as a portfolio being long equities, you can see you've lost money consistently over time. Now, why is it? Why is it that these equally volatile series, one goes up, one goes down? Well, it's very simple. If you're long equities, they pay off in good states of nature when marginal utility is low. Back during the tech bubble, you can see the blue line is well above the trend. That was a time when times were good. But during the financial crisis, you can kind of see it there toward the end. Bad times, your value of your equities went away, and vice versa for a portfolio that's short equity. That's like insurance. It pays off in bad states of nature. By the way, this graph is on a log scale, so maybe it's not so clear the difference in these lines. But if you invested $1 back in 1885 in portfolio long equities, it's worth about $2,600 today in real terms, adjusted for inflation. Government bonds, it's about $22. And short equities, it's about 15 cents. So it makes a huge difference whether things pay off in good states of nature or bad states of nature. Now this is a very interesting graph. It comes from a paper on, from a climate model, and it's representative of all of the climate modeling that is currently being done. What it shows on the vertical axis is the appropriate emissions price, and on the horizontal axis it shows what the authors labeled the income elasticity of marginal utility. It's basically the curvature of a utility function. And what they show is, as we increase risk aversion, the appropriate price for emissions goes down. Again, that makes no sense. The economists don't calibrate risk aversion for the obvious reason that if they increased risk aversion to be reflective of what we see in financial markets, it would show the appropriate price goes below zero, that we actually should be subsidizing fossil fuel emissions. Again, this makes no sense. Okay? We'll come back to that slide later. I also want to say what I'm telling you is not new to the profession. We're building on well-known things that are out there. Larry Summers and Richard Zeckhauser wrote a paper that showed a very simple model for pricing carbon. We're using that model. What we're doing is we're changing the utility function. Marty Weitzman, a professor at Harvard, has written about the fact that unknown risks haven't been included in these climate models. He points out that the essence of the emissions externality is not the known risks, it's the possibility for catastrophic damages. Frank Ackerman and a number of colleagues have written a paper about the limitation of the standard models used to analyze the appropriate price for carbon. These are called integrated assessment models. They're very complicated. They have many weaknesses, but in their paper, one of the weaknesses they focus on is the fact that the standard power utility function used in those models matches neither the risk-free rate of interest nor the equity risk premium. And finally, a couple of economists back in 1989, in analyzing the equity risk premium puzzle, said, you know, you can generalize the standard utility function. And they did, and this Epstein-Zinn utility function is what Kent and I are going to use. So let me tell you a little bit about utility functions. Utility functions basically are the way that economists model risk aversion. It's the curvature in the utility function. I'm afraid these slides, I don't know if you can see them better than I, but basically, the reason that higher curvature reflects higher risk aversion is because the marginal utility goes down as we increase income. What these utility functions have on the horizontal axis is either income or wealth. On the vertical axis, the utility associated with that income or wealth. And if you think about, let's say at the endpoints of these curves, maybe it's 100,000 on the right side, and I'm sorry, on the left side, and 300,000 on the right side, and 200,000 in the middle. Think about, would you be better off having a sure 200,000 or 100,000 or 300,000 based on the flip of a coin? Well, you're better off when marginal utility declines having the sure thing. And the more curved it is, the more you care to have the sure thing, the more you dislike having the uncertainty. Now, it turns out that people react very differently to changes in income at a point in time across different states of nature versus income through time. So when you think about the income that you have today versus income in the future, that's intertemporal substitution. And that's basically a trade-off of a sure thing today versus a sure thing in the future. And the more risk averse you are, the more curved is the utility function, the higher is the interest rate that you require. Basically, you recognize that you're likely to have higher consumption in the future because real incomes grow over time. And therefore, to the extent that your marginal utility is much higher today than it would be in the future, you require a higher interest rate to induce you to save. But the real interest rates that we observe in the economy are very low, and therefore, the curvature of a utility function to fit those nominal interest rates is very flat. On the other hand, if you want to fit the equity risk premium, you have to have a very curved utility function across income in different states of nature. And so, for that reason, the standard utility function has a very hard time fitting both low nominal interest rates and high equity risk premiums. This is actually the essence of the equity risk premium puzzle. There is no curvature that will price both of these at the same time. The standard utility function has the property that it uses, it's one-dimensional. It uses the same curvature across time and across states of nature. And what climate modelers do when they use the standard utility function is they use a very low degree of curvature. And so, for instance, Nicholas Stern, who wrote a report about 4 years ago, who was basically commissioned by the UK government to come up with a report on what's the appropriate climate policy, used a degree of risk aversion that would price the equity risk premium at about 12 basis points. 12 basis points are hundredths of a percent. So he's 30 times lower than the actual equity risk premium. The risk tolerance that's built into all these models is much too high, too much risk tolerance. It's inconsistent with the degree of risk aversion that we see in the markets. And why is that? Well, it's very simple. When you increase curvature in the standard utility function, it does two things. It increases the risk-free rate, and it also increases the equity risk premium. But it increases the risk-free rate faster than it increases the risk premium. And so if you think about discounting these future damages, you're discounting them at a higher rate. And even though the increase in risk aversion increases the difference between the risk-free rate and a risky rate, they both go up, and therefore the value of that is lower than it was with a flatter curve. Now, Epstein-Zinn is a way of solving that problem. Epstein-Zinn is a generalization of the utility function. It basically says you can have higher curvature across states of nature and lower curvature across time. And so this is just a more modern utility function that allows you to fit both the low real interest rates as well as the high equity risk premium. And all Kent and I have done is we've said, let's apply this Epstein-Zinn utility model in the context of price and climate. Following Marty Weitzman's suggestion, we include these unknown risks. We calibrate the emissions cost to a well-known study by McKinsey. We specify the Epstein-Zinn utility function, and we set the curvature over time in order to fit nominal interest rates, and we investigate what happens as we increase the curvature over states of nature, the risk aversion in that model. And then we solve for what is the optimal emissions policies. Now, the economic impacts depend very much on the uncertain outcomes of temperature. If you look at this graph, what we're looking at is basically the distribution of potential temperature outcomes in 40 years, that's the blue curve, and in 80 years, that's the red curve, assuming that we don't price emissions. And the horizontal axis, you can see there, it starts at basically 0, and then you get 2 degrees centigrade, 4 degrees centigrade, 6 degrees, and so on. As we go out that curve, we're talking about a world very different than the world we know, a world that's very uncertain, and it's very clear that the probability of something bad happening, some positive reinforcement, whether it's methane coming out of the tundra or something else going wrong that creates a tipping point, a positive feedback, something that will make this environment very unfriendly to humans and other species, goes up as we go out that curve. You can think of ordering different states of nature. I love the fact that economists talk about draws from a random distribution as states of nature. That's very appropriate here. We don't know what the state of nature is, how fragile the Earth's environment is. It may be that it's very robust, that we don't have to worry, that nothing would happen. But it's also the case that it may be more fragile and that something very bad will happen. So what Kent and I do is we basically assume that the probability of a climate catastrophe goes up with temperature. And then you make some assumptions about what happens if you get one of these bad draws. If there is a climate catastrophe, how much damage is being done? Now, one of the problems with the way economists have been modeling the price of emissions is that they assume that the damages are going to be very small because basically the known damages are very small. If you think about just the impact of bigger hurricanes, rising sea level, these are things that we can adapt to. This curve I'm showing here comes from a paper from Robert Pindyck called Uncertain Outcomes in Climate Change Policy. And like most economists, he basically in his paper is trying to represent the economist's view of the world. He says, you know, basically real income is going to grow at 2% a year as long as we can see, it always has. So 80 years from now, this is what we expect in 2090. People, if there's no climate damages, are going to be about 4.9 times better off in terms of consumption than we are today. Now, there may be some uncertain outcomes. There's a 10% chance that we might only be 4.7% better off. And in fact, 1 in 1,000 times, these economists think we might be only 4.2 times better off than we are today. Let me tell you, if that's the real nature of the risk, we shouldn't worry about it. Some scientists, I quote here Sherwood and Huber, say, perhaps recent estimates of the cost of unmitigated climate change are too low. Indeed, perhaps they're too low. What Kent and I have done is we've done what we added what risk managers call a fat tail. We have these climate catastrophes and we have significant damages associated with them. So we think there's a 10% chance that we might be only 4 times better off, and in fact, small probabilities that we might be 3 times or 2 times better off, or maybe 1 in 1,000 times we'll only be as well off as we are today. Now, maybe we're being too optimistic. Clearly, you never know. But you've got to take these potentially unknown risks into account. And what happens? Well, when you build in that Epstein-Zinn utility function and say what happens as risk aversion goes up, you get the blue curve. The appropriate price for climate emissions goes up with increasing risk aversion, as indeed it should. Now, Epstein-Zinn is a generalization. We can actually force the curvature to be the same across time and states of nature, and then we get the red curve over there on the left-hand side. Now, if you look carefully, I don't know if you can see this, but the horizontal axis on the left-hand graph goes from 0 to 60. because it takes about a risk aversion parameter of something like 30 or 60, some economists would say 100, to actually fit the extreme risk aversion built into the equity risk premium. So somewhere out there on the left-hand side is what's calibrated to what we see in financial markets. Again, I'm showing the standard model over there on the right-hand side. That scale goes from 0 to 3. And so the red line on the right-hand side is really duplicating what you see on the left-hand side. It's just an artifact of using the wrong utility function, one that cannot fit risk aversion. It cannot fit the financial markets. It can't fit the risk-free rate and the equity premium at the same time. Now, I wish these slides had come out better. But anyway, let's answer the 4 questions. So first of all, what's the appropriate price for emissions? Well, it depends on risk aversion. If you look at, and I don't know if you can see, these lines didn't come out very well. But anyway, there's a line up there, the dark purple line going up. That's inappropriate policy if you have very low risk aversion. It starts at about $15 and then over time increases to about $30 a ton. Now there's another line on there that I don't think is showing up very well. It's what happens if you increase risk aversion. It starts at about $50 and then comes down over time. Increasing risk aversion causes the discount rate to go down, and it causes the expected future returns on an investment, an insurance type investment, to come down over time. And what happens if we increase the risk aversion is that you price emissions high enough that you actually expect them to come down. The black line is what happens if we don't price emissions immediately. Well, 2 things happen. First of all, we continue to freely dispose of our emissions in the atmosphere. The atmosphere is like a reservoir. It has some capacity to absorb emissions safely, but a limited capacity, and in fact, we don't know what that capacity is. It may be that we've already overdone that, we've already used up that capacity. Let's hope not. There's hopefully some remaining capacity to safely absorb emissions, but we don't know what it is. The problem with not pricing emissions is that we just wastefully use up that capacity. And you can't put that back in the bottle. That increased risk is a legacy that we will leave for future generations. Plus, if we decide we're going to price emissions a few years down the road, having used up that capacity, the appropriate price at that time will be higher. Think about what the world would be like if we had priced emissions 20 years ago. We'd have a lot more capacity today. We would have a capital stock that would be emitting much less today, and the appropriate price today would be much lower than it is. As we go through time not pricing emissions, the appropriate price goes up exponentially. So finally, well, I want to actually, let me go back to that. The final question that I forgot to ask was, if your current price is 0 and the appropriate price is up here, let's say at something like $40 or $50 a ton, what's the appropriate path for emissions prices to go from their current level up to their future level? Well, you know, when you study economics at the University of Minnesota, you learn many good lessons. One of those lessons I remember very well because I learned it on one of the problems on my micro prelim. The problem was, it said, defend a policy of government smoothing oil prices. Now, this was back in the late 70s. We had just started the Strategic Petroleum Reserve. And I said, oh, I know how to solve that problem. I said, you know, I'm a macroeconomist. I know a lot about optimal control theory. I'll write down a stochastic economy. I'll bring in a feedback rule and smooth prices appropriately. It took me about 2 hours. I was very proud of what I had done. 0 credit. In fact, I flunked that prelim. I don't know if Herb Mowring is here, but it was his prelim, and he flunked me. I came in, it was 20 points for that question. I needed 5 points to pass the test. So I said, what's wrong with my answer? He says, well, Bob, the appropriate answer was, there is no legitimate defense of government smoothing oil prices. That's all you had to write. Full credit. 20 points. It was the legitimate that I had missed. It was implicit. What I had done is I had put prices in the utility function. I said, well, people are better off if, prices are smooth, or, well, no, what I learned was prices don't belong in the utility function. Allocations of resources belong in the utility function. So if you hear an economist saying, we ought to increase prices smoothly up to the appropriate level, no, that's wrong. Okay, so finally, let's summarize here. This is basically the bottom line on this. It's a cost-benefit analysis of climate policy. I'm looking at 3 different policies here. In blue is what economists call business as usual, not pricing emissions. The red is what happens if we price at a low value of risk aversion. The green is what happens if we price at a risk aversion consistent with what we see in the equity markets. And basically, we look at what happens today, what happens on average in 80 years, and what happens in the worst case. Well, if we don't price emissions, it doesn't cost us anything today. If we price emissions based on a less risk-averse utility function, we should spend about just a little less, 0.4% of consumption. That's pricing emissions just below, say, $20 a ton. And if we price at a risk aversion consistent with equities, that would be about $60 a ton, and that would be about 1.5% of current consumption. The impact on expected consumption isn't very different. What we have on the bottom is basically a graph showing states of nature across the horizontal axis, and they're ordered from bad to good as we go from left to right. So in our set of assumptions, most of the time, everything is pretty much okay. And so if we do nothing, the average impact on consumption is 4%. If we price emissions, it goes down to 2 and maybe 1.5%. It's really not that different. We're not worried about the expected. What we're worried about is the worst case. What if we get one of these bad draws? The Earth is more fragile than we thought. Well, if we do nothing, that's a 50% reduction. By worst case, by the way, this is 1 in 100. It's standard risk talk. It's a 1% worst outcome. 50% decline in consumption in 80 years versus if we do something today, we're basically insuring against that worst case. I think it's about 14.5% impact with the less risk-averse policy, 9.5% impact with the high risk-averse policy. So in summary, what did we do? We added a guess at unknown damages. We used this Epstein-Zinn utility function to calibrate both the real interest rate as well as the equity risk premium. We found that the optimal price for emissions goes up with increased risk, and it goes up with increased risk aversion. We saw that the forward price is also affected, that at high levels of risk aversion, the current price of emissions is high enough that it's expected to come down over time. And we saw that the price should go to the appropriate level immediately so that we don't wastefully use up our capacity to absorb emissions safely. What are the implications? Number one, economists should incorporate the potential damage from unknown risks. Number two, economists should use a utility function which can be calibrated to market prices, both the risk-free rate and the equity risk premium. And number three, economists should be very clear in their advice to the public, to businesses, and the government. Climate risk should be priced appropriately and immediately. So was President Calderon correct? Should we slam on the brakes? Yes, in fact, he was correct. We should. I would put it this way. We should price climate risk immediately at the appropriate level because not pricing risk leads to disasters. Thank you.